So he's a professor at Oregon State University, and I got to know him because he's one of the DARPA YFAs, Young Faculty Awards. We know our own esteemed YFA, Emilio, and so I met him at one of our DARPA meetings. His position is in like a school, like, I can't even remember all this, like oceans and environments and a whole bunch of stuff is in there. But the methods he uses are very innovative, and I think we'll have a lot of like applications in tons of other fields, lots of stuff that we work on. So yeah, thanks for coming, James.
Cool. Yeah, well, great. Thank you very much for inviting me down here, and thank you all for coming to see this talk on measuring and managing the complexity of social environmental systems. So this is what motivates me mostly. This figure should be familiar to all of us, right? So this is a little dated now. This is from the Intergovernmental Panel on Climate Change Assessment Report number 5. These results are from Earth system models that show our best efforts for understanding how the Earth might warm in the future in the coming decades and centuries. And there's a lot to this. This is a really intriguing story, but there's one story in here that's quite compelling, which is this. This is a modeled potential, right? And this is our worst case scenario in which the Earth will emit enough carbon that to the extent that the Earth is going to warm by 2 degrees Celsius by 2050, by 4 degrees Celsius by 2100. And then if you have the long view over centuries, this is 8 to 10 degrees Celsius warming. This kind of warming would likely be catastrophic. We would see large changes in the biophysical characteristic of our Earth, which would bleed into the ecosystem services that we depend upon for food security, defense against natural hazards, and even peace. Now, even if you think the likelihood of this scenario happening is very small, the costs are so large that there still remains a premium on developing plans that prepare us for a high carbon, high temperature world. The challenge is this: social environmental systems are complex, so there's many interacting parts, dynamic, and they often can exhibit these catastrophic changes. And they're multi-scale by nature, with emergent properties occurring at various scales. So this all makes it extremely difficult to predict the outcomes in social environmental systems. This talk is going to go through 3 things that I've been trying to do to get over this challenge. And it's kind of tautological. First, you need to characterize the complexity of the system that you're working with. And I'm actually going to talk about coastal marine metapopulations. Does anyone work on environmental issues in this room? Hands up. Anyone work on environmental things? Okay, great. The only one, that's fine. We'll go into, this will be a sort of a breathe through on marine ecology, where complexity is rife. After you characterize complexity, you should be able to predict the dynamics of your complex system. So here we're going to delve into, this is the DARPA YFA that I've been running for the last year. And this is applying manifold learning to a variety of complex systems. And we'll delve into a little bit about early warning signals of critical transitions. The last thing you need to do is when you characterize complexity and you figured out how to predict what happens in a complex system, you then need to make the step to design what you want. You wanted to be able to design, put in place incentives or features that lead to the emergence of properties that you want. And we'll talk about the multi-scale modeling of teams and more broadly cooperative behavior. Okay, so let's dive into the C with characterizing complexity for nearshore marine systems. So think of the nearshore, just out here on the coast. Think shallow water, 100 meters, just, you can see to the horizon. This is the sort of, it's not the blue ocean, it's the nearshore ocean. And I was doing this work as a PhD student in Santa Barbara. And like here, all along the Southern California coastline are these beautiful kelp forests. And kelp forests require rocky substrate on which to attach. And this is a map of rocky substrate. All I want you to get from this is that the rocky substrate is not uniform. It's quite sparse and patchy. This is important because the adult fish that inhabit these kelp forests don't move very much. They stay local to their reef. They have a very limited home range, ecologists call it. This is, however, in stark contrast to what they do as newborn larvae. So most of these organisms spawn little larvae, no bigger than, your small fingernails, smaller than that, of course. And they disperse with ocean currents. distances that are orders of magnitude greater than the distances they move as adults, so tens to hundreds of kilometers. That means if you go fishing off here, you go like spear fishing for lobster, say, the lobster you catch actually were born down in Mexico, in Baja. Okay, that's how far these organisms travel. And so the questions that nearshore ecologists always ask themselves are, well, what are patterns of larval dispersal and how do they connect different regions? I don't think this question is very difficult because the oceanography of nearshore regions is very complex, to want for a better word. So here I'm showing you modeled surface temperature for the Southern California bight in 96, 97, 98, and 99, produced from a regional ocean modeling system solution to this region created by Charles Dong, who was in the Jim McWilliams lab, which is in UCLA. It's one of the premier geophysical fluid dynamics labs in the world. And the movie was created by Satoshi Mitirai, part of the group that I was in when this work was being done. What I want you to see is in nearshore regions, there are these spatial structures, these eddies, these jets. There are some things called squirts. These are the features on which larvae disperse. And so how do we quantify larval connectivity given, yep.
Can you say again, was it the simulation?
It was a simulation, yeah.
Not an actual measurement.
Not an actual measurement, yeah. So this was a modeling solution, yeah. So we have hydrodynamic models that simulate the oceans, and this is
But from measurements, you just have some evidence that they have traveled so far, right?
And we have all different kinds of measurements. We have measurements of the biophysical properties of the ocean. And there are certain kinds of models that we can use those measurements to force your fluid dynamics model. We also have measurements of larvae. So we go out and we just catch them and we see where they are, if they are on fronts or in the middle of eddies.
So I guess my question is, how accurate are these models or simulations since you must have?
Generally, you can think of there are two classes of these kinds of fluid dynamics models. There are the sort of very primitive fluid dynamics physics type-based models that are still forced by data, but mostly by winds. That they have empirical data on which surface the winds blowing on the surface.
So that's the input data.
For this one, there are other models called assimilation models that use things like Kalman filters and other data assimilatory approaches to take in as much data as possible. So not just winds, but also like you have buoys, you have current measurements from boats, these kind of, maybe from boats, and then they're assimilated into a similar but different framework that does the best job we can at modeling the past. This is not modeling the past. This captures the statistics of the purely physics only models captures the statistics of a particular region, but then the assimilatory models actually try and recreate, okay, there was an El Nino at this place at this time, because it's more data driven. Okay, so then, given that we have these models, we can answer this question about how do we quantify larval connectivity. You can use those very same hydrodynamic models within which you can simulate the dispersal of larvae using what are called Lagrangian particle simulation. And here I'm showing some output from one such simulation produced by Dave Siegel, who was my PhD mentor, advisor in Santa Barbara, and Satoshi, who was the postdoc at the time. He's now at the Okinawa Institute for Science and Technology. To cut a very long story short, all of this work leads you to quantifying something called potential larval connectivity, which is nothing more than yes?
So I assume, maybe I asked, that vast majority of larvae don't end up in the force die.
Yeah. So this thing called potential larval connectivity is a conditional probability of a larvae going from place I to place J, kelp forest I to kelp forest J, given that it was spawned at a particular time and that it could survive dispersing around in the oceans. And if you sum up over destinations over J, you get a number less than 1 because a large fraction of them die. They wash away. And actually, there's a really cool evolutionary question there. Like, why would you evolve this strategy if most of your babies die? That's a different story, though. Our estimates of potential larval connectivity, so this probability of going from kelp forest 1 to kelp forest 2 varies with species. It's asymmetric. So, going from here to there is not the same as going from there to here. It's heterogeneous, and really importantly, and I won't go into this in much detail, but this is a nice property of these connectivity matrices. It really does vary in time because it's based on fluid dynamics. The connectivity this year is going to be very different from the connectivity next year.
As necessary. But and the fluid dynamics and the temperature depends. So there's the, you mentioned evolution, but there's no this edge, the spread when temperature is like peaceful.
Yeah, exactly. So the expected or even the individual experience, temperature experience of a larvae moving around in the ocean is very important. It determines the rate at which they grow. Because if they're traveling around, they can be out for half a year, moving, dispersing with the ocean currents, and so they're growing. But when they're born, they're tiny. When they come back, if they're lucky to a kelp forest, they're big. They're bigger at least. So the thermal experience greatly determines their size and then survival when they land. So one use of potential larval connectivity when I was doing this work was motivated by this guy, right? So this guy was in charge of California when I was around in Santa Barbara, and he put in place the Marine Life Protection Act, where marine protected areas, so areas of the ocean that are off limits to fishing, went in throughout the California coastline. Okay, and when you do design marine protected areas, there are normally two sort of philosophies behind it. You can either put them in place for conservation, or you can actually put them in place for profit. I wanted to do something different. I wanted to actually see if we can design marine protected areas in the Southern California Bight so that we could avoid catastrophes, because when I was doing this work, Deepwater Horizon oil spill was occurring. And I thought to myself, if a catastrophe were to happen down in San Clemente Island, I don't know, the Navy does some explosions or something, the mortality there would actually be, because of larval dispersal, be experienced somewhere else, in a diminishment in the adult population somewhere else. So the claim we wanted to explore was because of potential connectivity is spatially heterogeneous, with some nearshore regions more important than others with regards to metapopulation robustness. So ecologists use the term metapopulation to describe a system of Southern California Bight that's comprised of little subpopulations. So the metapopulation is the population of populations comprised of little subpopulations. These are the individual kelp forests. Now, to test this or to investigate this claim, we developed a spatially explicit metapopulation model. And it's very simple. It's a very simple integer difference model that said if I know the abundance of a certain fish at a given place and some estimate of its fecundity, I can know how many babies are made. With my estimates from my fluid dynamics models of potential connectivity, I can estimate the fraction of those babies that were born there that go over here. I can estimate how many survive. These are all the good questions that you've just asked. And then sort of recruit, join the adult population at the other place, and then make more babies. So this was a dynamical model in which this potential connectivity was embedded, and it allows me to create simulations to explore the potential impacts of a catastrophe. Not necessarily an oil spill, that's not the best example, but some catastrophe that knocks out the population down there, down here, down there, and so on and so forth. So this is what I did. I'm going to show you the results on the x-axis. Well, I'm going to impose 100% mortality at specific places, collapsing the local fish stock and continuing to do so until there are just no more fish at all in the whole system. On the x-axis is the fraction of the coastline that I've removed, and the y-axis is the abundance as a fraction of the pristine case. And I'm going to show you a few lines. I'm going to focus on the blue line is when I pick these little kelp forests to destroy at random. It's random, so I do it many times. I have an envelope, and no surprise, as I nuke little places, the more and more the whole system collapses after some time. The alternative, though, is what if I pick the places, the kelp forests, based upon their centrality? In this case, eigenvector centrality. In this case, you can collapse the regional metapopulation way more quickly. In fact, it's the quickest way you can do it. You guys are probably very familiar with centrality, but when I explain this to my ecology colleagues, I say that LAX is a hub of air traffic, right? And Corvallis Airport is not a hub of air traffic. I mean, this is literally like if you go to Google Maps and you drive, and you look at Corvallis Airport, there is a dust storm occurring at the airport, right? So this is the idea. It's not air traffic, but larval traffic, right? So by using centrality to take out places, I'm taking out the main connectors. And so when the governator says, find me 13% of the coast to protect, do you miss him? Maybe not, I don't know. we can look up those most central places and plot them on a map for a given species. And I would argue that if you wanted to avoid a catastrophe occurring for this species based upon its larval dispersal, don't let these places go. Okay. Now, there's a whole host of other uses for potential connectivity. It explains patterns of genetic dissimilarity amongst places around the world for both nearshore fish, but also globally for phytoplankton. It's a really important source of stochasticity, which is important for fisheries, and so on and so forth. So this is one example of what we do in my lab to try and characterize connectivity. The second part of this talk,
I want to ask you more about the graph that you formed, actually. So you said directed graph, and what are the nodes in the graph?
So the nodes are the places. There was one, when I had the movie of the particles moving around. On the next slide, there were these different places.
So you just discretize space into like just contiguous.
Yep. Yeah, non-overlapping cells, and then you release the particles in the fluid dynamics model, and you simply calculate the fraction of those particles released that went from here to there for all places.
And it's dynamic because it's always changing, right?
Yeah, and well, for this work, I'll be honest and say we use a time average connectivity matrix. In some other work, we looked at some time changing matrices to explore the impact of that stochasticity, as it were, on population dynamics.
So, but once you time average, what you get, like just a connected graph?
Well, it might be fully connected, but it's the weights that are really important. You still have heterogeneity in how strong you place it. Okay, so characterizing connectivity, now talking about predicting dynamics. We obviously want to know when certain events will happen in the future, and for marine ecologists, I've talked to you about one case study, but it could be coral reefs too. Coral reefs are known to flip between hard coral-dominated states. This is the one we all kind of love and want, but they can flip if perturbed by a hurricane or by dynamite fishing. These kinds of perturbations can knock them into an algal-dominated state. These flips between alternative dynamic regimes occur also in financial systems, we think, and in geopolitical systems too, from states of peace to states of conflict. And prediction can be easy, especially if you're a physicist. Sorry, this didn't mean to insult anyone in the room, Greg. But if you work in nature, it can be more difficult. And if you work with social systems, it can be actually nearly impossible. At least it appears to be so. But it does depend upon what you want. Many systems exhibit, yes, sudden shifts between alternative dynamic regimes. These changes start locally and through contagion, spread globally, and they're multi-scale in nature. What we need for these systems for observing and even anticipating multi-scale change is early ability to detect early on that the contagion has started, at least locally. But even before then, we might be able to see whether the system is primed for multi-scale change. Turns out there are a suite of early warning signals that exist. They're based upon bifurcation theory and something called critical slowing down. You can measure critical slowing down in time series by changes in variance or correlation. But here's the deal. It doesn't always work. It doesn't always work in large part, I think, because of multi-scale dynamics. By this, I mean, in the past, we've been limited in our studies to macroscopic variables. So if I'm an ecologist, I look at the population abundance of a given species here in the Southern California bike, or I watch a financial market index. I get information on this, and then these early warning signals based upon critical slowing down are applied to these time series one at a time. You look down the time series to observe these changes. Today, we live in an age of big data, though. We can do something different. We can collect microscopic variables, the condition and behavior of individuals that comprise a system. And instead of looking down time series, you can look across them. And you can look across them and characterize the relationships between these microscopic agents at a given time. And what we're doing in this DARPA YFA is to use manifold learning to measure the geometry of that system over time, as defined by the relationships between the microscopic agents. And so you quantify the geometry of a system, and you observe it changing over time. And the idea is that the changes in the geometry not only indicate, but might even precede a large shift in the system. So I'm going to give you 3 examples of this. A simple example of correlation in financial markets, something called diffusion maps applied to collective behavior in nature, and spectral graph wavelets applied to human mobility from data from mobile phones. So financial markets, can we anticipate a crash using simple correlations? You go to the Wharton School in our case and download S&P 500 returns. They look something like this over a particular time period. At a given time, you take a little snippet out, a little short time series snippet, and you look at the cross correlation between pairs of stocks. And the idea here is, this is naive, but the idea here is that from complex systems theory, complex systems, if they become over-connected or highly connected, contagion has the potential to occur, and the potential for instability goes up. And so this is what we're naively trying to look for in this. So here's a result from 1990 to, sorry.
When you say contagion, you really mean cascade.
Fine, yes.
And then are you assuming what model of contagion are you using? Like just an independent cascade model?
I'm using it more loose, way loosely right now, just to term that, like, if the behavioral change of one actor will induce the behavioral change of another. Independently. Or, well, no.
Each neighbor can independently cause you to change.
Right, okay. Okay, so here are some results. Time on the x-axis from 1990, and then the mean cross-correlation, so taking the average over pairs of cross-correlations between all stocks through time. And what you can see, there are these distinct peaks that occurred just after these major crashes. 1997, there's an Asian market crash, dot-com bubble in around 2002, then there's 2008, Eurozone 1, Eurozone. I did this up to Donald Trump's election. I haven't gone further. Been too scared to. But the idea is this. These reactions in the market in terms of the cross correlations occurs after the perturbation. Okay? So this is not giving us any early warning signal that something was going on. The system's not becoming overconnected, not becoming unstable, at least measured by these correlations. This is instead a reaction of the market to the perturbation. And as Greg pointed out in the DARPA meeting a while ago, this is essentially all the stocks dropping down in value. Okay. But so, can we do something different with manifold learning? So you go back to the same data sets, S&P 500 returns, take a small snippet in time, and instead of looking at the cross correlations, you calculate an affinity matrix. Yes.
I wonder if you know you're seeing that.
Yeah. Yeah.
So of course, finance, but maybe there's similar models. Which could be happening.
Yeah, we're very aware of his work. We could talk about it at length afterwards. Yeah. So take a snippet of data, calculate the affinity between pairs of stocks, and you can use different metrics for affinity. But here's what we do: we use diffusion maps, and I will go into diffusion maps in a little bit more detail in just a few slides. So hold off questions just for now. But affinity matrix, diffusion maps, and you can look at the geometry of the system by using diffusion maps. And there are different metric or measures one might use, and but if you do so, you do over time, you can track how the geometry of the system changes. And so this is one result that we have for one particular measure of geometry, what we're calling system size. I don't want to go into too much detail. I just wanted to use this as an example to show that this particular measure of geometry has a property of an early warning signal, at least for these two giant perturbations, the dot-com bubble in 2002 and 2008. The size of the S&P 500 rapidly sort of increases many months before the nominal peak of these crashes. So this could be considered an early warning signal. It could also be, yeah.
Can it be just indicator that shows that the markets actually are very well before actually crashing?
Could be, yeah.
But in the years before 2008, it was doing really well, and it's almost zero in the best part, right? People were making the most money later on. Okay.
Well, so yeah, we haven't actually investigated it in such detailed terms. We were just trying to interpret this in terms of what the system might be doing. And when the system size is small, all the nodes are very much closer to each other. And this can be thought of like the system becoming, if everything's close together, this could be interpreted as a system becoming connected. So to the story of whether the system's becoming overconnected or not, leading to potential instability. This is one way we're trying to measure that. So whether that's an early warning signal or actually the bottoming out in system size preceding it is the early warning signal that the system is primed for multi-scale change. We don't have an answer yet. We're just observing these changes empirically with newish geometric measures. So this is just the tee up actually. So in conclusion, by looking at the interaction between microscale agents, in this case stock returns, one can identify objective macroscale variables that potentially reveal early warning signals of catastrophic events. This is by no means complete. This stuff we're just starting to get a handle on. But this is other work that we're digging into using similar tools. So this is a study of collective behavior in nature. Can we anticipate shifts in collective behavior? And what I'm speaking about are data on fish schooling. So this is a video recording of golden shiner fish. They're about the size of your small finger. And they were filmed in the Cousin Lab in Princeton, which is where I was for a few years. What the guys did was they created a very shallow 2D fishbowl, essentially. And so they're confined to this 2D layer. And they put them in there, and they just naturally exhibit three forms of collective behavior. They sort of circle around together. They will move in the same direction. And then they mill around and around in sort of random directions. And they constantly transition between these three behavioral states. So the question is, can we classify and then anticipate shifts in collective behavior in this data set? Like the stock markets, the first step, and the most important step, is quantifying or coming up with a measure of affinity between individuals. And for this data set, and actually all the other data sets too, you could use a variety. You could just use spatial distance as a measure of affinity. You could look at correlation and heading. You could look at some velocity, these kinds of things. But if you do that, then you're in a place to start using diffusion maps to classify and predict changes in behavior in a new way. So this is what we have done. By we, I mean Matt Titus here, who's in the audience, who's done all of this work, essentially. So you can ask him questions if there are any sticking points. The point is, yes, you start by putting a metric on your data, calculating an affinity between individuals. You use the diffusion maps to essentially model the diffusion of heat on the network, and this translates your raw data into a new set of diffusion coordinates that better organizes your data. So this is actually what we did for the stock markets, but this is what we did new was to do it again with a different metric. Do the whole process again, calculate the affinity, do the diffusion maps, create a set of diffusion coordinates. But what Matt did, that was a big innovative step, was to then compare the sets of diffusion coordinates using something called a map alignment statistic. Now, in a bit more detail, so diffusion maps create a set of diffusion coordinates from a given affinity. And we do that, in this case, for the fish using two affinities based on velocity and spatial location. We compare diffusion coordinates from the two affinities by measuring the scale of projection, their scale of projections. And under the null hypothesis, this is a beta random variable. The map alignment statistic, ZK, is a weighted average of the normalized projection statistics. And in sum, this gives us essentially what is can be considered a p-value that measures the likelihood that the two diffusion maps exhibit common large-scale structures by chance. So I've just blasted through that, but what that all ends up doing essentially is giving us a way to classify the different collective behavioral states of the school through time. So that's the map alignment statistic through time. Okay. Yeah.
The large-scale behavior is qualitative, right? But your statistic is giving a probability of being in one of these qualitative states, whether they're exhibiting the same qualitative state. Is that
Did you want to take his question?
And so here you can see in the red we've marked out what we call swarming, which is unorganized behavior. And so that red the flat line because you choose a threshold. So you take that continuum statistic, you say if this is less than 3, we're going to say that those two coordinate systems.
So there's a measure of organization.
Yeah. there's other work that goes into separating out what organized states, what those distinct organized states.
Thanks, Matt. Thank you. Okay, so there's Matt. In conclusion, for this part, manifold learning through the application of diffusion maps helps to classify different modes of collective behavior. It also identifies variables that provide early detection of shifts in modes of collective behavior. And I haven't shown you this work, but this is something that we're working on. So still within the sort of the genre of prediction, this is the last case study, human mobility. People make strategic choices about where to go and when, and we want to know whether we can classify and predict changes in human mobility. So we're changing up completely here. We're going from a 2D fish tank to Senegal. Okay, so this is on the northwest coast of Africa. Dakar is the capital on the far west there. And I want you to draw your attention to this place in the middle called Touba. This is a place of religious worship, and people migrate there at several points in the year for religious purposes. There are also large-scale seasonal changes in human mobility related to agriculture. And so this is the system that we have data for. We have call detail record data, so CDR data, for the whole year of 2003. This is from the Orange telecommunications provider. So 1,666 nodes, so the cell towers, and then Orange tracks 300,000 random users every 2 weeks. So there is new random users every 2 weeks. That counts up to around 3.6 billion text calls in the year. From all of that data, you can build a dynamic mobility network, the fraction of people that went from here to there, essentially, for a given day, say, through time. What our goal was to develop a multi-scale tool for identifying the dominant modes, or indeed the dominant scales of human mobility. And the answer that we came up with was to use spectral graph wavelets. So given a sort of daily evolving human mobility graph, you have an affinity matrix. From that, you fit out the graph Laplacian. And then from that, you construct wavelets as kernels of operators. I'm jumping over a lot of work, but that ultimately ends up with a wavelet function. For each city, you have a wavelet function over the other cities as a function of scale. In this particular investigation of religious migration from Touba, we choose Touba as that place and identify the dominant scale for each day's mobility. And from that, we extract the corresponding wavelet function on all the other cities and cluster over time. And this leads to this time series here. So this is day of the year, and this is the wavelet scale. And the colors are the clustering using just simply k-means applied to the wavelet functions over other cities, other cell towers. What this analysis identified is, yes, there's actually a normal part of the year and there's a seasonal part of the year corresponding pretty much spot on with changes in the rainy season. But it also picks up these larger scale sort of religious movements, and then we can actually plot these. So averaging wavelet functions per cluster, we can show them spatially. So this is the wavelet function in Senegal for normal mobility. This is for religious mobility. You can plot them, but it's hard to see how they differ. So we also plot the absolute difference between the wavelet functions associated with these different forms of human mobility. So this is the religious mobility minus the normal mobility. And what the reds are identifying, it's picking up Touba as the dominant place, but it's also identifying these places way out in the countryside where people's mobility has changed as they migrate to Touba for this religious event. Yes.
I mean, to what degree are the ones on the edges simply noise? Because if you don't get much migration information, it's possible to look for it.
Okay, we have not quantified the relative change, the change relative to the background noise.
Although, I mean, the central one, whatever is
Touba, yeah. Yeah. Well, maybe this. I mean, qualitatively, this might be informative. So, right, at least when we do this, we see these nodes light up in the sticks. When we look at a different set of wavelet functions, so this is the seasonal wavelet function minus the normal wavelet function, we get a very different plot, identifying changes in mobility relating to the coast. So although I haven't quantitatively judged any of these plots against, say, the noise, they are qualitatively obviously different from one another. Okay, so in conclusion, a short intro to this work. Spectral graph wavelets can be used to essentially denoise dynamic networks as a function of scale, and this has helped us to identify the dominant modes, the dominant scales of human mobility. The next work that we're doing in this area is to identify permanent displacement caused by, in this case, large flooding that occurred during that year from temporary migration using manifold matching. And Zach Gelbaum is the other postdoc in the DARPA YFA project working on this, but he couldn't be here today. So in sum, on this topic of prediction, if you have data on fundamental microscopic variables governing the relationships between individuals, you can use tools from manifold learning to identify useful macroscopic variables. These macroscopic variables can help identify different dynamical regimes or states, and we think provide early detection and early warning of large changes in complex systems. So last part of the talk, characterizing complexity, dealing with it to try and predict large changes in your system. With that, you might say, okay, now what do I do? How do I design things so that I get what I want out of a particular system? We're going to focus on cooperation across scales of organization, answering the question, when do people work together for a common good? So, I've shown you pictures of fish schooling. This is analogous to birds flocking. In nature, organisms do this all the time. Birds flock together, form a collective to improve their individual fitness. Indeed, we humans do this in a whole range of things. This is a picture of Alaska fishermen bumping into each other sometimes, some groups working together, some guys not, to improve their catch. So too for our governance institutions that are meant to work collectively, cooperatively for our betterment, but like in the case of the US Senate, it actually more mirrors like a competitive sports system where you have groups forming teams to compete against each other. And indeed, that is the focus for some of our future work on competitive systems. So we're thinking about military systems, business systems, sports, esports, essentially teams. And we have some data for this. So this is player location data in addition to the ball for a soccer match in the UK that we have and will be analyzing. These systems are really tricky because unlike the fish that we've analyzed before, where we've assumed every fish is the same, agents in these systems have highly specific roles, are very strategic, and are constantly looking to innovate, and weird things happen. So this was Manchester City in 2016. Their squad was, I think it was the most expensive squad in the world at almost £500 million British pounds. And they came fourth. And they lost to these guys, Leicester City, whose value was an order of magnitude less and were nobodies the year before. So these weird things happen, and we want to know why. We're also looking at esports, so we've been scraping data from Destiny 2, and a lot of the tools that we've been working on for the analysis of fish, say, and human mobility, so wavelets, spectral graph wavelets, are being advanced to provide us information about leadership in these teams. So Zach has been working on something called wavelet centrality, which is actually being proven to be analogous to leadership centrality, which is a recent known measure of centrality. That's all in the future. We haven't actually started that work, but this is some work that we have been working on. In my lab, do some work on collective action agreements. So developing multi-scale models of action to explore when good agreements over sustainability or carbon emissions can be made. And these models, these situations depend upon mechanisms to overcome free riding. So the free rider problem is when individuals in a population consume more than their fair share of a common resource at no extra cost. It's a problem associated with public goods and common pool resources. So to economists, this is like their bread and butter. If you want to understand a multi-scale system, people working together for sustainability or limiting carbon emissions, you have to solve the free rider problem. This is known, also known as the tragedy of the commons. Garrett Hardin in the 60s worked a lot on this. He was at UC Santa Barbara, and this is a fundamental problem that we're trying to deal with. You essentially have two ways of dealing with the tragedy of the commons or the free rider problem. You can either use a stick and punish the free rider, or you can use the carrot. You can create, reward the agent that acts cooperatively. And we've been exploring social and financial instruments as the carrot to incentivize good behaviors, and in particular, we've been focusing on risk. So I don't know if you know this, but food producers around the world are exposed to massive amounts of risk. So this is data on the semi-deviation variance in production and revenue for fisheries, aquaculture, and farming alternatives in Alaska. What that means is I have an expectation of how much money I'm going to make, and if I'm a fisherman, that could be almost half at any given year. It's almost like being a soft money researcher. So you can use this, though, to incentivize good behaviors. We've been exploring the idea of information cliques. That is, so we developed an agent-based model of fishermen and fish. So the fish are the heat map, the fishermen are the little dots moving around trying to eat up the fish. And you modulate, you change the amount of information that they share between each other. And then you measure sort of the benefits of that in terms of how much fish they catch and the variance in how much fish they accrue over time. Those simulations can be used to develop models of the change in behavioral state of your agent, so whether I am cooperative or not, whether I share information or not, and that allows you to back out the benefits of cooperation. And this is just one result that I'm showing that just says the benefits of cooperation only occur in these kinds of fishery systems when it's hard to find fish, and if when I find fish, it's also hard to pull them out. And this makes total sense if you've ever been fishing. If my buddy shouts he's found some fish over there, it's only worth my time going over there if by the time I get there, there's any fish left. And also that I don't bump into any other fish along the way. So there's sort of very straightforward results from these analyses, but that can be useful for designing mechanisms for encouraging information sharing amongst natural resource users. Just one slide to this. This is work that I'm doing just now. We're looking at insurance, actually, as a tool for encouraging cooperation amongst resource users. So we've developed a model of insurance for aquaculturalists in Myanmar, and insurance is very straightforward. You pay a premium, so the total amount of money that you make goes down, but your risk is greatly reduced. And you can use that as an incentive for people to join what we're calling a risk club, where fishermen pool their money into a pot, and that is used for the insurance. Okay, so in conclusion, designing multi-scale properties. To manage complex systems, one must be able to design multi-scale properties. I think that's just a given. Many tools can be brought to bear on this. We've been using game theory, so dealing with the tragedy of the commons and agent-based models. But we are also going to be applying these geometric learning tools to competitive sports-like systems. And for socio-environmental systems, there are many solutions that are on the table. You can use information sharing or insurance, for example. All right, in closing, we live in social environmental systems that are complex. There are multiple connected working parts. They are dynamic with alternative dynamical regimes, bifurcations between them, hysteresis, path dependence. And there's multi-scale, contagion or cascade, and cross-scale feedbacks. This all makes predicting outcomes in complex systems really hard, and that's a challenge because politicians often come up to us and say, well, tell me what the future is going to look like at some point. And it's a really hard question to answer. A better question to ask would be, how can we prosper actually under uncertainty? The tautological response is, well, we need to design resilience. That's the ability to cope with change. One very conceptual piece of work that I'm trying to push forward is this: designing governance institutions modeled on the vertebrate immune system. Now, this might seem way out there, but the vertebrate immune system is an incredible system that has evolved over several, many years, millions of years, to defend itself against a host of known, unknown, and unknown unknowns, right? It comprises of a few things that might be familiar to us now. Early warning signals that there is a problem. It then buys us there's a general response that buys us time for an adaptive response that is then remembered. It is also distributed. There is no central commander controlling our immune system. These things make it incredibly resilient, and I would argue that governance institutions modeled after the vertebrate immune system is what we need for coping with uncertainty. If we can do that, we can change the challenges that we're facing into opportunities for sustained prosperity. Thanks very much. Questions?
The African wavelet example, am I right? Is there a graph there that you find implicitly based on spatial distribution, or are the wavelets in the continuous domain, and then you lift this to somehow learn the migration pattern on the graph?
Now you might want to correct me if I'm wrong here. Bogus, did you want to jump in?
Sure. The networks that we're using is based on the human migration.
Okay, so the network edges are based off of the migration signal.
Yeah.
So wait, network edges are just based on locations that people are individually.
So the nodes are the cell towers, so places in space on the landscape, and then we just measure.
So the network is based on cell towers?
Yeah, the nodes are the cell towers, and the edge weights are the fraction of people that traveled from this place to that place.
So you don't incorporate the actual the calls, the links in the front calls?
No.
No, because it's
just the number. In this case, I think it was just purely the number of texts, actually. And so this is the thing, it's a very rich data set. You could use voice calls as well. You could use duration of calls. You could explore this. You can construct a whole number of different graphs, actually. And one thing that we wanted to investigate that we still might is that the information, right, so that's important. You can get calls from here to there, but you can also measure people moving from there here by the details. We're just working on the latter. You could construct an information network, which is people making calls, and changes in that you would imagine would precede the actual mobility. I'm going to call my family, say there's a flood coming, can I come stay with you? That should happen.
But the mobility signal is also moderated by the geographic terrain, assuming that people don't fly. Assuming people only move, constrained to
roads and things.
Roads and can't go over certain mountains and things like that.
Yeah.
So there should be a secondary strong signal from that as well in your mobility data. Right? So I don't know. How do you think you could separate them, or do you think it's not a good choice to separate them, that they're somehow confounded with each other?
Yeah, I think you could, and I would go to a different data set. I'm pretty sure you could get like a roadmap for Senegal and come up with like a least cost path, or just some path between pairs of nodes. If they had Google Maps, one could do that. I don't know. But then I compare that network to the actual the mobility data from the mobile phone data.
Thank you.
So I missed a little part. I don't know if what I'm going to ask is related to what I missed, but so I really appreciate the fact that you're bringing the environment into the equation, because most part people will be looking at system, be looking at social and the technical aspects. So what's your view of the role of technology in this system, right? I mean, all of the things that you described are somewhat, the technology, it maybe can be used for measurements, like in the ocean metapopulation examples and so on. But when you talk about human systems, mobility, last example, financial systems and so on, technology has a major role. People communicate, people spread information on these platforms from one another, and so lulti-scale, primary scale, and so on. So where does that technology come back to the equation?
I'll give you two things to think about, right? Which one I'm pretty sure you'll be familiar with. Financial markets, right? Over the time period that we analyzed, the S&P 500 going back to the 90s, you've seen this incredible change in the technology used by traders to make trades, right? high-frequency trading, algorithmic trading. And so the system's non-stationary completely because technology is changing. So that's at a fundamental level, I think, what technology does. It makes the systems that we live in, we're studying, non-stationary. And you need to keep that in mind. Doing equilibrium analysis, you've got to take that with a pinch of salt. The other example that I'll mention is stuff that I haven't talked about, but it's fundamental. It's a new project based on NASA. And we have the location of fishing boat, the majority of the world's maritime vessels, their location every 10 minutes or so globally for the last 5 years. And we're trying to employ a lot of the tools that we've developed for the fish, agents in space moving around, reacting to one another to try and identify what are called dark fleets. These are fleets that don't transmit their GPS coordinates, but are moving in and around visible fleets who are acting legally. These dark fleets commit all kinds of horrendous things, from arms trafficking, drugs trafficking, slave labor for fishing, these kinds of things. The role of information here is really key. Over the last decade or two, we've seen the increase in technologies that people use to communicate. Right? So this is mobile phones in Senegal. In fishing boats, they are like you can have Chinese fishing boats on the other side of the Pacific communicating with each other, strategizing about where to go and to do what. And so this is a really real challenge for us because in the fish system, your affinity could be is related to just spatial proximity. I can assume that I'm talking to you because you're very close to me. I'm not talking to the guy down the road far away from me. But in this world of highly connected communication, I could be communicating through this screen here to somebody in China. And that means you need a different coordinate system to observe who's connected to who. And that's super hard. It's hard to do. Yeah. So I think that would be what I would say about how technology is changing the problems that we're trying to deal with.
I do have a follow-up.
Okay, that's good.
So some of the things that came to mind are sort of the constraints. It's sort of a follow-up to what you're saying, right? So in the example of the migration of this larvae, you get that essentially they don't have any freedom of will, right? I mean, they do what the currents do. If you think of the social system, social technical system, people exhibit all sorts of behaviors. And depending on what the system allows, you can observe emergence of different phenomena, right? So at some point, Facebook stops, maybe Twitter stops, deactivating points, or Facebook stops censoring, news, and then you have all emergence of all these misinformation campaigns, and those affects the stock markets, those affect the elections, and so on. So this global scale politics, global scale policy, and this can directly influence the phenomena that you observe. So I think in these modeling systems, when you are looking at least sort of the high level, microdynamics model, maybe put the ingredient of the role of technology in information system should be explicitly sort of coded and not just maybe just the sort of the change of coordinate that you were describing. We can bring it to lunch as a own discussion, but it's a big question.
I mean, I would say this, that I think about this as an ecologist actually. When you talk about larvae and they sort of have fixed behaviors, they just move around with the ocean currents. That's true on the ecological timescales. There is evolution occurring. So these larvae, these species, they do slowly evolve to longer abilities to stay in the ocean, shorter abilities. But that is Darwinian evolution, so slow mutations, changing sort of this direction, that direction. What it appears to me is that in social technological systems, the mutations can be huge and are continuously, can occur at a much. You can't have this separation of timescales, ecological and evolutionary. The evolutionary timescales in socio-technological systems are occurring at the same time. Companies are constantly looking to innovate. This is evolution, right? Innovate new ideas, new things that'll catch and stick and grow. So that the mutation variance is high. I can come with a completely new idea, and it might take hold and grow rapidly. And that's distinct from purely biological systems as well.
So for the financial market example, so you can try to predict the amount of of those kind of keys only. But I kind of relate to what you were saying. So these things exist in the larger, larger system. So you consider using other variables actually. So for instance, now for financial predictive models use social signals like or other places. So
we've thought of everything from, well, we've not thought of everything, but we're considering, things as simple as interest rates, but also we actually got, and we could all use it. So you go to Zillow and get the housing Z index or the housing price data. It goes through quite a long time series, over 2008. And we know from 2008 that there was this connection between the housing market crash, which occurred a little bit earlier, 2007, and this financial crash, because all the banks were sort of in lots, playing around with debt in funky ways. So the short answer is yes. The long answer is like, well, then how do you do that? I have another, you could imagine that I have two complex systems, sort of financial markets, and the window into that is my data on S&P 500 or a few other variables. But then I've got the housing market data too, and I have my only lens there. The window into that data set is my Zillow data set. You might be able to say, okay, there's some sort of shape to these data sets, a manifold that you can learn through geometric techniques. But then do you want to compare? How do you compare them? Can you come up with causal inferences too? Does this changes in the housing market be creating changes in the financial markets too? We haven't dealt with that, but we've been thinking about along these lines too.
Okay, are there any other questions? All right, well, let's thanks James and Matt again. Oh yeah, there's
Are you guys familiar with